In this module, we will see how and why we need power processing in electric drives. And we will call these power processing units, and so in short, PPUs. So what is the role of these PPUs and how we can zero in on a switching power pole and use that as a building block. And we'll see how we can control these power processing units through this pulse width modulation type control, and we will look at their average model in this segment here. So let's begin. So we are talking about these power processing units, and what we really have is utility in most cases on one side here and a machine on this side. And quite often the power flows from the utility to the machine, but that need not be the case. For example, in wind turbines, this machine really is a generator, and the power would be flowing this way over here into the utility. So the structure that has come about is shown here, and whatever we do has to be done very efficiently. Okay, so here let's here it's called a rectifier, which takes this AC utility, whether it's single phase or three phase, and it converts it into a DC across a large capacitor, as shown here. And I have shown a symbol of diode rectifier, and that can of course be used, but in that case the power can only flow from here to in this direction here. So if you want the power to be bidirectional through this system, and especially if you want this power to flow from right to left here, then this converter, so to speak, could be very similar to the switch mode converter that is shown on this side here. And both of these would be controlled by this controller over here. So we can see as sub blocks here, we have one converter here which converts AC into DC and AC to DC. And then we have another converter which converts DC to the form required by the motor. So motor is a sort of a very specific term. We should call it a machine, and it could be a motor or a generator. So we'll see how this power processing unit works here. So let's take a case of this DC motor drive, and we were just looking at the right-hand side of that block diagram we saw earlier. So let's say that we have that DC voltage across that large capacitor, and what we are trying to do is to control this output voltage here across this DC motor and this current over here. And again, like I mentioned to you, power flow could be this way or it could be this way here. Similarly, let's take the case of so in this case we have two switching power poles here, and we will discuss that more in detail. And similarly, when it comes to AC motor drives, we have three such power poles here. So in this case, we have a DC voltage across this large capacitor, and we have to synthesize AC voltages at these terminals with respect to this motor neutral. And once again, the power flow could be in either direction here. All right. So like I mentioned to you, that this switching power pole is really the basic building block. And the requirements are that it's embedded. It's a bipositional switch, either up or down. And there's a voltage port on one side. So this large capacitor forms this voltage port. And then you have this inductor, which forms the current port. And this is the voltage across this current port labeled here. So let's call this point A, which is connected to the switch, and the negative DC bus, let's call this N over here. And then we have the switching function, Q sub A, which controls the switch up or down. When Q sub A is 1, let's say, the switch is up, and when it's 0, then the switch is down, right? That type of thing. So that can be done in this comparator shown here, and we'll talk more about that here. Okay. So let's see what goes on in this comparator. We have a control voltage. So this control voltage has to be generated somehow. And so these are signal level voltages. And in this comparator, this control voltage is compared with a triangular waveform signal, V triangular over here. And as you can see, when this control voltage is higher than the triangular waveform, then this switching signal is 1. And when it's lower in this region over here, then the switching signal is 0 over here. And if you go back to the previous slide, when this switch is in the up position, when Q sub A is equal to 1, then the voltage at the current port is equal to Vd. And when this switching signal is equal to 0 and the switch is in the down position, then the voltage is equal to 0 here. So you can see that we can define the voltage at the current port by this expression here. Q sub A times the input DC voltage Vd, and Q sub A is taking a value of 1 or 0 like this. So the voltage across the voltage current port I should say looks like this, and it has this average value shown dotted over here, and this is indicated by putting a bar on top of this voltage symbol over here. And you can see that we can define the switch duty ratio. So duty ratio means the time the switch is in the up position as compared to the entire switching time period. And this is happening at a very high frequency, let's say 10 to 20 or even 50 kilohertz. So the switching time period, if the switching frequency is 20 kilohertz, would be only 50 microseconds for 20 kilohertz. So you can see that we can say that for the duty ratio times the switching time period, the switch is in the up position, and if you have the switching time period defined here, then for the rest of the time it's 0 here and 0 over here, right? So that's the meaning of this switching duty ratio. The time interval during which the switch is in the up position divided by the switching time period T sub S, which is inverse of the switching frequency here. All right. So it's very easy to see that in this type of comparison here, the average voltage across the current port would be equal to the input DC voltage coming in and times the duty ratio of the switch. And by controlling this duty ratio, we can then control this average value here. And this duty ratio here is the control voltage divided by this peak value of the triangular waveform here. And you can immediately see that if we substitute this over here, we can say that the average voltage that appears at the current port is this amplified control voltage, and we can think of that as the gain of this pole, which is the input DC voltage divided by this peak of this triangular waveform, which is used for generating these switching signals here. So that's this gain of the pole is listed over here. All right. So we will come up with an average model, as we'll see in the next slide, but we have to realize that what is appearing across this current port here is really a pulsating waveform. It's going all the way from Vd to 0 and back to Vd, right, in every switching time period over here. So as a consequence, and this is the switching signal, and so what, as a consequence, what happens is that the current that flows here wouldn't be purely DC. But let's assume that the inductance is enough here, and ideally we have a current which is purely DC current here, equal to its average value. So this is not going to happen, but let's just assume if it were to be the case and the ripple is negligible, then what would be this current here coming from the DC bus? Well, you can see that. It will be equal to this output current when the switch is in the up position. So it will be like this here when the switch is up, and when the switch is in the down position, it will go down to 0 here. So this will also pulsate like this, and this current would also have an average value, which is indicated once again here by this dotted line, but by a bar on top of IDA. So it's IDA with a bar on top over here to indicate average, right? But in the real world, this current IA would have some pulsation, as shown here by this waveform here, which will have this average value, which we are trying to control, this average value over here. All right. So we have to recognize that since the voltage across the current port is not a DC voltage or a low frequency AC, as we'll see, we will have harmonics in this voltage at the current port. And let's say if you are producing DC, at least that was the intent, to produce an average DC, then these harmonics would be at the switching frequency, at twice the switching frequency, and so on. And if this switching frequency is high, for example, I gave a value 20 kilohertz as an example, then all these harmonics are at very high frequency, which can be easily filtered, or which may not result in significant ripple in that current that we were talking about, current through the inductor. So this is in case when you're trying to produce a DC voltage at the output, whereas if you are trying to produce some low frequency, let's say F1 was 60 hertz, but you still have the switching frequency of 20 kilohertz, then what will happen is around the switching frequency and its multiples here, we'll see some sidebands. And sidebands would be related to the switching frequency by some expression like this. So we have to be aware of the fact that there will be harmonics, and by properly designing these converters and selecting the switching frequency, we can minimize their effects. All right. So the average model, if you forget about the switching information, what is going on here is that you have a voltage port across which we have this voltage, and then we have a current port on the right side, and we have this current through that. So this VP represents the voltage port, and CP represents the subscript CP, represents the current port here. And you can see that basically this voltage that appears, average voltage that appears across the current port, is related to the voltage that appears, which we have at the voltage port. So V sub CP average is this duty ratio, which could be varying as a function of time. So you can put a function of t everywhere here, times VVP average, and similarly IVP average. This current that is drawn from the DC, from the voltage port side is related to current that flows on average through the current port here. So you can see that this relationship that we have can be represented by a transformer like this, and it can pass DC as well as AC, because this is really a mathematical representation. A physical transformer, of course, cannot pass DC, but this is just a mathematical representation. So we use this symbol as shown here. For DC, a straight line; for an AC, a bar like this. And this is really an ideal transformer with controllable turns ratios. And this turns ratio is 1 to the duty cycle, D, and that D is controlled by the comparison of this control voltage coming in to V triangular hat. So this D is V control, or VC, times divided by V triangular hat here, like this here. Okay. The main thing to notice is that this transformer can pass DC as well as AC as well as DC, but voltages are unipolar. So this voltage is always of this polarity, and this voltage is always of this polarity. We'll see later on this current can reverse direction in this way, and this can reverse and be flowing that way. So that is not a restriction, but the polarities of these two voltages must be unipolar here. So what this is, again, that is reiterated over here, that in the switching power pole, this voltage VAN is positive, and of course this is of this polarity here, but this IA here can reverse. So if the average voltage you are producing here is greater than this is a circuit, a representation of a DC motor, for example, and we'll see later on. If the average voltage you are producing across the current port is greater than this induced EMF within the DC motor EA, then the current here IA would be greater than 0 with the direction shown. So this direction shown is like this here. With that direction, it will be greater than 0, and the power would flow from here to here. Okay, so this is called a buck mode because this voltage average would be always less than this voltage over here, right? So power is flowing from a higher voltage to the lower voltage. So this is called a buck mode. Whereas if you can make this voltage, average voltage, to be greater than this E sub A, I'm sorry, less than, if you can make this less than E sub A, then this current here would reverse direction. It will be less than 0 under this condition here, and then power would flow from here to this VD. Okay, so VD is always the largest voltage here, but in this case, so-called boost mode, this VAN average is made to be less than EA. Okay, so you can see from a in this overall circuit, from a smaller voltage here, power is flowing to a bigger voltage over here. So this becomes a boost converter. So this switching power pole would allow us to make the current flow in either direction here. And then we can also calculate the ripple in this current, and that is shown here. This is the pulsating voltage that appears across this DC motor equivalent circuit, and we can use superposition here. We can calculate its average value, which is indicated by this uppercase letter here, and inductance plays no role. So we can calculate IA, and if you subtract this average value from this pulsating waveform, what remains is the ripple voltage. And in that case, you can forget about the resistance, and of course the DC voltage, because we're using superposition, would disappear. But this resistance, you can of course include that, but it's so small that it's negligible compared to the reactance of this inductor over here. So we can just neglect that. So that's what is shown over here, that we can calculate what the peak-to-peak ripple here would be. Of course, the average value is given by this circuit here, and peak-to-peak ripple in this current can be calculated by plotting this ripple voltage, where we subtract the average value of this voltage from this actual pulsating waveform. So it looks like this, and corresponding to that, the ripple current would look like this, which has no DC average, and you add that ripple current to this average value, and you get the total current here. So you can see that in this circuit, the current would not be a pure DC at the current port, rather it will be, it will have some ripple as shown here. So how do we implement this bipositional switch, which is going up or down? Well, we implement that by using 2 transistors and 2 diodes. So one transistor diode pair makes up the buck converter, and it's let's say switched by this switching signal over here. And if you take the complement of that switching signal, that is then controlling the other pair made up of these 2 devices. So that complement here then controls this transistor over here. So you can see that when this current is positive, either this device would conduct or this device would conduct. But if this current were to become negative, let me erase all link here. If this current were to be flowing in this direction, then only this transistor would conduct when it is gated on, and when it's turned off, this current would flow through this diode over here. So, and again, it's going from a lower voltage on the right-hand side to a bigger voltage on the at the output here, so to speak. So it's really a boost mode of operation here. So we quite often we use MOSFETs or IGBTs, as will be described later on, and the switching frequencies could be easily in some range like this here. But the idea is that we must keep the switching losses low, because every time a transistor goes from on state to off state to on state here, there will be some switching loss, and approximate trajectory is shown. And similarly, when it goes from on state to off state, there will be some switching loss, and the trajectory is shown once again. So we want to keep that switching loss on an average very small. And also we want to keep the conduction loss in these devices small. That means in their on state, they should have very low voltage drop across them. Okay, so that brings us to the end of this segment where we saw the overall structure of a motor drive, where we need this power processing unit, because we have often a utility voltage on one side, and on the other side we have a DC motor or a generator or an AC motor or a generator where the frequencies may be different. So we need this power processing unit. So we saw its role, and we saw that this switching power pole, which is just a bipositional switch up or down, embedded within this two-port, voltage port on one side and current port on the other side is needed. And we just analyze that switching power pole in detail once, and then we can use it repeatedly. So that will be the advantage. And we can control the voltages and currents associated with this power pole by pulse width modulation. By adjusting the pulse width, we can modulate. And then we also saw that how we can represent this switching power pole by an ideal transformer with a controllable turns ratio.